Hello everyone, this is Shaoxuan Lai from Sanyasang University. I'm glad today to present our research paper titled Explore Your Network in Minutes, a rapid prototyping toolkit for understanding neural networks with visual analytics. I will begin by introducing the motivation behind our research work, followed by an overview of the two main components of our work, the abstract model and the programming toolkit. I will then provide two examples to illustrate our approach and conclude with a summary and some future work. Past practice have demonstrated that visualization is intuitive and effective for understanding the internal mechanism of neural networks. However, the effort for developing such visual analytics systems could be demanding. Existing visual analytics systems for neural networks are often designed for specific architectures to answer specific questions. However, users often struggle to conduct their customized explorations effectively when using these works, and designing such visual analytics interfaces are challenging for non-visualization experts. Our goals are to support visualization experts in their rapid prototyping before developing a sophisticated system, and to provide non-experts with a way of raw visualization code development so that they at least have something to explore and explain their networks. To support researchers of different backgrounds in understanding various architectures based on distinct assumptions, we need to first summarize the existing visual analytics systems, and then represent the existing systems in an abstract common form. Finally, develop a prototyping tool to realize the representation. From a visualization design perspective, we believe that a visual analytics interface is defined by the relevant data, the relationship between different data, and the interactions on the interface. To determine the content of our subsequent work, we conducted a survey of existing literature in this field. Here we use transformation to describe the relationship between data. Based on this survey, we generalized all the data related to visual analytics for neural networks using tensor data, and we describe all interactions as modifications to the data. Based on a summary of commonalities and the survey, we designed an abstract model to represent these commonalities and developed a programming toolkit based on this abstract model for building interfaces. Next, I will introduce our abstract model. When designing the model, our concern is that the model needs to represent the three kinds of key ingredients and enable researchers to easily establish connections between components in the model and those in an interface. So we choose a flowchart format. I will now explain how we represent each of the three ingredients. Our model is centered around the data and focuses on the dimensions of tensor data. We use rounded rectangles to represent data and color boxes to represent the specific dimensions of the data. Within the color boxes, we use different colors to differentiate between dimensions with different semantic types and letters to further denote specific semantic meanings. We use these units to represent the data associated with all the views in the interface. For data that is not directly associated with a view, a model optionally omits them. We use arrows with icons to represent the transformation between data. Different letters on the icons denote different types of transformations. Specifically, the filter transformation refers to selecting a subset of data along a certain dimension. We use a different type of arrow to represent the interactions in the interface. As mentioned before, color boxes represent the specific dimensions of the data. Each interaction arrow starts from a color box or an interaction widget, indicating the retrieval of a subset of the dimension, or obtaining information from the interaction widget. When an interaction arrow starts from a color box, it signifies the presence of an interaction in the related view that enables selection of a subset in that dimension. Each interaction arrow ends at a rounded rectangle, transformation icon, or color box representing the modification of the corresponding object using the carried information. When applied to a color box, it represents the modification of the subset information of the corresponding dimension. Whenever the subset information is modified, the elements corresponding to the subset will be highlighted. The interactive arrows imply the modification of the subset information of their starting color box. The information carried by the interaction arrow may undergo certain mappings before its ending, which we denote with a green icon with the letter M. Next, I will demonstrate how to use the abstract model to represent a prototype of LSTM-Vs step by step. We can first represent the data bound to views on the interface. This component represents a parallel coordinates plot that displays a two-dimensional hidden layer data. Here, H represents the size of the hidden layer, and I represents the length of the input sentence. This component represents a view used to further filter the selected dimensions. These three components correspond to the selected paragraph as well as the match count and part of speech of the words within the paragraphs. I will provide a more detailed explanation of this model later. Then we add transformation related to the above data. The three views at the bottom are derived from three collections representing words, match count, and part of speech filtered by the same filter. These three collections are not displayed on the interface, so we use the aforementioned simplified format to represent them. After that, we represent the interactions on the interface, including the interaction of selecting subsets of dimensions on the parallel coordinates plot, and the interaction of obtaining match count and selected word indices on the selected dimension view. Next, I will introduce NNVis Builder, the programming toolkit we have designed based on the abstract model. NNVis Builder utilized a client-server architecture, where the client employs D3 code to render visual elements, and the server employs Python code to handle data-related tasks. We have encapsulated the process of generating client-side visualization code from data, as well as encapsulated certain aspects of data processing on the server side based on the abstract model. Here is an example of using NNVis Builder to build a prototype of LSTM-Vs. Next, I will explain each part of the code combining with the model. The code presented here defines a parallel coordinates plot and a selected dimensions view using the related data. Users can directly define different types of views from existing data. If users need to access the hidden layers, parameters, and other network data, they can do so through the Builder instance. Before generating the views, users can perform some data pre-processing. For example, in this component, a subset is selected from all the dimensions, and a paragraph is chosen from the corpus. Then a parallel coordinate plot is defined. In this component, we define the view for further filtering the selected dimensions. When defining the data for this view, we only specify the data type, and the value of the data will be generated during the interaction process. The code presented here showcases the use of data transformations. The regions C, D, and E represent the selected words along with their match count and part of speech. They can be seen as three different attributes of the same objects, obtained through the same filtering transformation from three different attribute collections. This component defines the filter. This component defines the three attribute collections. Here the match count is computed during the interaction process. This component applies the filter to these collections and obtains the resulting data. Then this component defines corresponding views using the resulting data. The following code defines the interactions on the interface. These interactions include filtering out a subset of dimensions from the parallel coordinates plot and matching corresponding paragraphs after further filtering in the selected dimension view. This component describes the interaction on the parallel coordinates plot, where the arrow indicates using the selected subset of hidden dimensions to modify the data in another view. Therefore, the selected dimension view will display the hidden dimensions selected from the parallel coordinates plot. Besides, the lines corresponding to the selected hidden dimensions in the parallel coordinates plot will be highlighted. This component describes the interactions on the selected dimension view. In the event handler, the match count for each word is first calculated, and the match count collection is modified accordingly. Then, based on the sorted match count, the indices of words with higher match count are obtained, and the filter is modified using this result. This way, every time an interaction occurs, the match count and the selected words will be updated. The following flowchart summarizes the data flow during the interaction process. When an interaction action occurs, the selector of the view is responsible for generating the selected subset corresponding to the interaction action. Besides, multi-selector can be used to form complex selection pattern. This selected subset is then used to modify other data, transformation, or subset information. When the modification leads to changes in the data or subset information of other views, the views will be redrawn or highlighted. That is the complete process of interaction. Then, I will present two examples that demonstrate the correspondence between interfaces, models, and code. The first example is a prototype of the TensorFlow program that we built. The three components, A, B, and C, represent decision boundaries of different layers, connections between layers, and labels of the original data. Two filters are applied to the training steps and hidden layer output channels. The second example is a customized visual analytics interface for CNN. The components of the model A to F corresponds to the interface and code. As you can see, to generate such an interactive interface that visualizes multiple pieces of information, we do not need to write a lot of code. Finally, I will make a conclusion, analyze the limitations of our work, and discuss some future work. Our work includes an abstract model and a programming toolkit, an NVIS builder. By combining the abstract model and the programming toolkit, we provide a comprehensive solution that enables users to rapidly build prototypes of visual analytics interfaces for neural networks. This approach may empower researchers in the machine learning community to explore and analyze their networks effectively, foster innovation, and advance the field of network visualization. However, our work still has some limitations. When designing an NVIS builder, we focus more on its generalities for different network types, and it currently does not support dynamically modifying the network structure during the interaction process. We may resolve this issue by adapting additional code for different networks. Besides, we adapt a client-server architecture and use D3 for element rendering, which can result in performance bottlenecks. We may consider migrating the rendering process to the GPU in future iterations. Lastly, we intend to design a visual programming system based on the abstract model and the programming toolkit, enabling users to build interfaces based on the abstract model with little code. Thank you for your attention. Now I'm pleased to take your questions.